Okay, so welcome. This is now lecture number 13 for Math 140 Business, October 12th. And today, this week, will be a review week for the test. That will be a week from today. 267709045. Okay. So let's first make sure we're clear on what this test covers. And then we'll start reviewing for it. Okay. So test October 19th on chapters 1, 2, 3, 4, 5, 9, 8. Don't want to skip 8. 1, 2, 5, 8, 9, 11, and 15. I also got an email today from my supervisor. I asked him a few questions and he wanted me to remind everyone. He says, make sure to remind them to complete the health screening survey the day of the exam. So complete health screening survey day of exam. Otherwise, don't think you'd be allowed to come. Wear a mask. Bring ID.
Do we have to wear the mask during the test?
I would be surprised if the answer to that was no. Because otherwise, why you have the mask? I mean, you'll be in a room with lots of other people in a confined space, right? I mean, I personally don't like wearing masks, but I recognize that they're the thing to do at times. So yeah. Is that a problem? Do we have a problem taking the test with masks on?
No.
Yes, no, I mean, you know, this is the school policy. So those are the three things to do before. I mean, wear a mask, bring ID, you know, because I don't know who you guys are. I don't even see half your, forget half, like 99% of your faces. So yeah, definitely do that. And the health screening survey the day of the exam, you certainly have to do. Okay. So what we're going to do is we're going to work backwards with the newer stuff, the more complicated stuff. I'm going to open the Math 140 Business Workbook. And I'm going to go to chapter 15 in the workbook. And we're going to do those questions and then work through it and work backwards. And we'll try to cover at least hopefully 15 and 11 today. So let's find chapter 15 in the workbook. The workbook is not labeled by chapters, is it? That's really annoying. So what? I don't even have my book with me today. Let's see. That was okay. We didn't do those. Anyone recall? I'm not looking at the chat if anyone's typing, but does anyone recall what 15 was about? It was sampling stuff, right?
Yeah, it was sampling distribution for proportion.
Oh, but the last thing we did was probability. That was 15, right?
Yeah, last thing was probability.
Okay, here we go. So we're gonna do that first because probability gives people problems. So we're gonna start with that one. Okay. So let's start review. So this is a 15 review. We'll start working backwards. 15 review. This is from the workbook. So if you have the workbook, which you should have because I posted it and hopefully you downloaded it at some point in the past, we are now on page 70 of the workbook. And let's go through these questions. The faster we answer them, the faster we can move on. So question number 1. If you flip a fair coin, 1A, if you flip a fair coin, so heads on one side, tails on the back, if you flip a fair coin, what is the approximate probability that it lands with the head side face up? Probability that it lands with the head side face up. This one,
50%.
yeah, 50%. I think the reason why they say approximate probability is because they are taking into account the very unlikely chance that it lands on its edge or it just hovers forever or some nonsense like that. But really, it's just probability of heads. B, does this mean that if you flip a coin 10 times, you will definitely have exactly 5 heads and 5 tails?
No.
No.
No, certainly not. C, does this mean that if you flip a coin 10 times, you will probably have exactly 5 heads and 5 tails?
Yeah.
Yes.
Actually, the answer to this is still no. And the reason is as follows. If you flip a coin 10 times, what are the possible number of heads? What are the possible number of heads that you might have if you flip a coin 10 times?
10.
No, that's not 10, it's actually 11. Because you can have 0 heads, 1 head, 2 head, all the way through 10 heads, correct?
Yes.
So there's actually 11 chances. Now, those 11 chances, those 11 outcomes are not equally likely. You're much more likely to have 5 than you are to have 4 or 3 or 2 or 1 or 0, correct?
Yes.
But the question is, are you more likely to have 5 versus having anything else? If you add up all the other possibilities, is 5 still more likely than any of them?
No.
No.
No, in fact, I can compute, although we haven't learned this yet, but I can very quickly in my calculator compute the likelihood of getting precisely 10 heads, which is about 24.6% of getting 5 heads. So there's roughly a 24.6% chance of getting 5 heads, which means probably I won't get 5 and 5. Probably I'll get something else. But of the 10 outcomes, it's still the most likely one. Does that make sense?
Yes.
Okay. And D, does this mean that if you flip a coin 1,000 times, you'll probably have around 500 heads and 500 tails?
No.
Actually, this one is yes. Okay, this one is the law of large numbers, right? The law of large numbers says I cannot predict with any certainty what I'm going to get for any one flip. But if I flip it a lot of times, I'll probably have something in the vicinity of what I expect, which is 500 each.
And it gets closer and closer, right? The more you do it.
Yes, it converges in the language of calculus. It converges to 0.5, but I mean, in theory, I can flip a coin 1,000 times to get 0 heads. That's a possibility. It's just unlikely for that scenario to occur. The most likely scenario is that I'm somewhere in the vicinity of 500, 500. So Anahi, does that make sense?
Yes.
Okay. Okay. So that answers question number 1. Question 2. Probability is important in statistics, which is what this course is all about, primarily because many statistical studies involve a sample drawn from a population. Therefore, chance is involved, right? We don't know the outcome that we're going to get before we actually do the experiments. And when you don't know the likelihood, when you don't know the outcome of what you're going to get, you have to ask, well, how likely is this outcome? How likely is that outcome? And that's what probability is all about. So A, among Americans aged 25 or older, 32% have a bachelor's degree or higher. So 32%, the probability of a bachelor or more is equal to 0.32. Suppose a simple random sample, suppose an SRS of Americans 25-year-old or older is taken, which is the population under consideration. What is the probability that a particular member of the sample has a bachelor's degree or higher? one person, what's the probability that that one person has a bachelor's degree or higher? This goes for everyone. 32% have a bachelor's degree or higher. If I pick one person, what is the probability that that one person will have a bachelor's degree or higher?
1 over 0.32, I'm guessing.
Why 1 over 0.32? First of all, wait, hold on a second. Do me a favor, take out your calculator. What is 1 over 0.32?
3.125.
How can the probability be 2.1 something, whatever you just said? And I think that was wrong also. It shouldn't be 3 point something.
Wait, so you're looking for a fraction, you said?
I'm looking for the answer to the question, but when I asked for the probability, somebody said 1 over 0.32. 1 over 0.32 is bigger than 1. How can a probability be larger than 1? That's like one of our first rules of probability, wasn't it?
Yes.
So it can't be 1 over 0.32.
Would it be 32%?
Yeah, it's just 0.32. If 32% of people have a bachelor's degree or higher, and I pick one of them at random, then the likelihood that that one person has a bachelor's degree or higher is just 32%.
Yeah, I think the only thing that kind of confused me there was the age group, because I wasn't sure if you're still taking from the population.
Yeah, so the age group was the population under consideration,
Oh, okay then.
right? So this is because I'm not going to include children because, you know,
Yeah.
they're going to college. It doesn't make sense. Okay, now B. Next question. An SRS of 50 companies listed on the New York Stock Exchange is taken. Okay, so an SRS of 50 companies listed on the New York Stock Exchange is taken. Suppose that 62% of all stocks listed on the New York Stock Exchange gained value in the past month. 62% of stocks gained value. So, what is the chance that any particular company in the sample has gained value?
62%.
Well, I'm pretty sure that's what they want here. But of course, it's kind of a bad example because a company is not going to necessarily have just one stock under consideration. They're going to have a portfolio. So it's really a silly question. But if we change it to the probability that any specific stock gained value, then the answer, yes, would be 0.62.
Okay.
Okay, it's really a bad question. And then C, let me read it first. Okay, so an SRS of, this one is a better question. An SRS of 50 companies is taken. 8 of them stock split last year. 8 of them stock split. Now, we don't need to care what a stock split is. It's just something that occurs in the stock market every now and again. So of the 50 of them, huh?
Nvidia recently did it.
Yeah, it happens all the time. It's just for those of us who are not necessarily stock market oriented, it doesn't matter. But the SRS of 50 was taken, 8 of them stock split next year. Watsco Incorporated, which by the way was not in that sample. The question is, what is the probability that Watsco had a stock split? So we took an SRS of 50, 8 of them had stock splits. Then I picked some random company, Watsco Incorporated, and I'm curious, what is the probability that Watsco Incorporated had a stock split? What would the answer be?
16%.
16%. 8 out of 50. 16 over 100, 16%. In other words, the sample gave us a 16% stock split likelihood. If I take any one stock or any one company, then that's the best estimate I have for how likely it is that a company would do a stock split. That's what the SRS does. That's why I take a sample in the first place, because I want to infer something about the population from it. Does that make sense?
Yes.
All right, question number 3. A. What is the probability that you will earn a grade of K instead of A, B, C, D, or F in this class? So at the end of this class period, you check your grade, and the question is, what is the probability that your transcript says K?
0.
0. It's not an option. Okay, B. What is the probability that you are going to take a breath in the next 5 minutes?
100%.
Percent.
Well, I'm going to say approximately 100%, because there is always a possibility that, the world ends right
Yes.
now. Oh, it didn't happen. But how about right? Oh, it didn't happen. Well, how about right? You know what I'm getting at. All right. So if you put 100% exactly, I would give you credit, but technically it's about 100%. Right? Impossible. Certain. That's why all probabilities must be between 0 and 1. All right. Question number 4. Write the sample space for the experiment of flipping 2 coins. Use H for heads and T for tails. What is your sample space for flipping 2 coins?
Heads, heads. Heads, tails. Tails, tails. And then flipped. So, well, TH.
Anything else?
Does the flip still apply with HH and TT or no?
Well, HH means heads on the first, heads on the second.
it'd be
What would the flip of that be?
it'd be a different coin.
You're
Like-
flipping, wait a second, you're flipping 2 coins. So we'll call the first coin coin 1, and we'll call the second coin coin 2.
Okay, so it'd just be coin 1 was H, and then coin 2 would be H.
Okay, that's this one.
And okay, so it would just be 4 then.
Okay, just 4 of them. Okay. So A, what is the probability that if you flip 2 ordinary coins, you'll get tails, tails, heads, heads, whoops, or heads, tails? What is the probability that if you flip 2 coins,
3 out of 4.
3 out of 4, because they are equally likely outcomes? Because they are equally likely outcomes, 3 of the 4 of them give you what you want, and done. Next, if you roll a die, once, 1 roll, what is the probability that it won't be a 6?
5 out of 6.
5 out of 6. Okay, I'm not getting a lot of people answering. It's the same voices I keep hearing, but hopefully those of you who are the silent majority are agreeing with this and it's making sense.
I have a question. So on the test, is it always going to be asking about equal outcomes? Like,
No, no. What if I ask you the likelihood of having 5 boys if you have 7 children? Is every outcome of 0 boys, 1 boys, 2, 3, 4, 5, 6, and 7 equally likely?
No.
No, and therefore you can't just say, oh, it's just going to be 5 out of 8, 0 to 7, 8 possibilities, or 1 out of 8.
Would that be 50-50, or is there like other?
There's a little bit more involved. I think one year I actually taught that chapter, And it was, I later realized it wasn't on the syllabus, and you know, I thought it was important to know, but it wasn't on the syllabus, so they said don't teach it because they don't need to know that. You know, they're very big on not just being organic and teaching, you know, whatever you think of, or tangents and things that are similar and things that give you the overall picture, but rather they need to know this, they need to know this, they need to know this type thing. So you know, I try to stay on the path, the narrow path as much as I can. I deviate sometimes. Can't help myself, but for the most part, I try to stay. This one, I'd be more than happy to explain it to you if you come to office hours or something, but I don't think I'll do it in class. And if you just want to look it up online, it is called the binomial distribution. It's very interesting and very important. But anyways, until we do it in class, let's not worry about it. So question 5. Rachel is at a party. Ooh, Rachel. Rachel's boyfriend, William, has promised to show up at the party sometime between 9 p.m. and 10 p.m. If William keeps his promise, but the time he arrived during that hour is completely random, then the appropriate probability model for the situation is a uniform distribution with the following curve. It's uniform, that means it's the same height everywhere, because any outcome is as equally likely as any other. And it goes from 9 to 10 because those are the only possibilities, 9 through 10. So my curve looks like this. Well, not like that, but like this. And like this. And here's 9, and here's 10. So the question is, shade in the event William arrives between 9:50 and 10. Shade in the event William arrives nightly between 9:50 and 10. Where would I shade for that one?
Like
Almost towards the end.
Sorry, I heard both of you at once. Anahi, you were saying something?
I was gonna say a little bit to the left of 10, up to 10.
So where should I start?
Yeah,
Specifically?
like right there is good.
Okay, so I'll
That should be.
say this here.
Yeah.
Okay, so if we assume this is 9:50, then that's it. Now, what is the probability that I land somewhere between 9:50 and 10?
One out of 6.
1 out of 6. Do we agree?
Yeah.
Okay, because when it comes to continuous distributions, it's about the shaded area divided by total area. All right. Hopefully everyone's making everything's making sense. Everyone's getting it. Let's move on. Question 6. Assume that non-fasting glucose levels in females aged 20 to 29-year-olds who do not have diabetes. Wow. Non-fasting glucose levels, females 20 to 29 who do not have diabetes. So that's 4 restrictions on the population, and we're measuring these glucose levels. And we're told that it follows a normal distribution. A normal distribution, we know what it looks like. It looks like this. What's the mean based upon this distribution? Hopefully you're all staring at the same thing I am on the workbook, and you're not just waiting for me to write things down.
120.
Is it at the middle point?
Yeah, 120 right in the middle.
Wow, I'm so sorry.
And well, let's not go that far. And I'm just kidding. What is, or am I? I don't know. What is the standard deviation approximately based upon this picture? If you had to make a guess. Come on, smart guy, you got this. What's the standard deviation? Uh-oh. Silence. I didn't offend you, did I? I was just kidding. You there?
No, I just don't know the answer.
Ah. Okay.
I'm thinking.
Okay. This goes for everyone. Based upon the diagram, the picture, what is the standard deviation?
88.
Wow, not even close. Where do you get 88 from?
It's like the shaded area.
32.
No. No.
16.
16, that's correct. Who's the real smart guy? Why is it 16?
I just saw the difference between each number.
Oh, damn. Sucked.
Sorry.
Should have said yes then. Okay, give me a better reason why it's 16. We definitely went over this. I definitely did it. Why is it 16? Does that help? No, yes, maybe so. What's the geometric representation of the standard deviation?
When the hill starts looking like a bowl.
When the hill starts looking like a bowl. And where does that occur? Right around there or so, right?
Yeah.
Well, look at the picture in question 6, which is better than my approximation. When you say that it's right around 136 or 104, that it reaches that point, give or take.
Yes.
That's why it's 16. Make sense? Yes, no, maybe so?
Yes.
Okay. So the shaded region starts at 90. It told me that in the problem. The shaded region starts, here's 88. But the shaded region starts at 90. Okay. So A, the shaded region represents the probability that what? This goes for everyone. The shaded region represents the probability that what?
Glucose levels is lower than 90
Yeah. Well, for who? Give me more, be more specific.
for women that don't have diabetes or all the other.
That's not what I'm looking for. I'm looking for something specific.
Woman between the age of 20 to 29.
Which women between the age of that?
Who do not have diabetes.
Well, again, those are all the considerations. That's the population. That's fine. And that's all necessary. But it's not what I'm going for. The shaded
The
region.
non-fasting glucose level.
No. The shaded region represents the probability that a randomly chosen female aged 20 to 29 who does not have diabetes will have a non-fasting glucose level below 90. It's the random female the random, person that I'm picking. And that's important to say because if you have somebody in mind who has it or does not have it, it's not a probability question. The probability comes into play when you don't know what the outcome is going to be. The person has to be randomly chosen. A randomly chosen female with all these considerations will be lower than 90. Does that make sense?
Yes.
Okay, is that clear why what you said earlier didn't quite qualify? Everyone? Everyone else?
Yeah.
Okay. So B.
Yeah.
Okay, so a randomly chosen so-and-so, so-and-so, so-and-so. B. Estimate this probability by I, what percent is that approximately? And let's not do it by I, let's do it as best we can by the 67 or 68, 95, 99.7 rule. You guys remember that rule?
Yes.
So let's do it.
So I think it's so on the 88, it's 95% because it's
Okay.
2 standard deviations away.
Okay,
So it's a little bit less than that.
so what's your answer?
94.8.
Okay, so you say, I want to see if I get this straight. You say that the blue region represents 94.8% of the area under the curve.
That's not what I meant, but
Okay, so then that can't be right, correct?
we're talking about the shaded region, the percentage of it, right?
Yes.
I see. Okay. I'm looking at it totally different.
Okay, okay.
Okay, let me try to do it again.
2.5.
2.5%, much better. But I would refine that a little bit. See, 2.5% is from what number on down?
Sorry, what?
2.5% will be from what number on down?
Oh, the 95%.
No. Answer my question, huh? Say that?
It would be from 88 to
It will
0.
be from 88 on down. Because 88 is the 2 deviations out. Agreed?
Yeah.
So 2.5% would be from 88. But I want it from 90. So what's a better answer than 2.5%?
Three percent.
Okay, approximately 3%. That sounds a little better. Just something a little more than 2.5. Yes, no?
Yes.
Okay. C. Let X be the non-fasting glucose level of a randomly selected female, aged 20 to 29 years old, who do not have. Wow. Okay, we need a grammar check here. Who do not have diabetes. Is X a continuous random variable? Explain. If it's not continuous, what is it?
It's continuous.
Sorry, yes, but what's the name that we have for something that's not continuous?
Um,
I like this continuous. It is technically correct, but it's not what we called it. What do we call a non-continuous random variable? Anyone recall? I am so
Oh, I think it's
dismayed.
what would you say?
I thought I'm so
It's
dismayed.
finite.
Well, no, not finite. We call it something else. Maybe I'll have to ask that on a test. It's called discrete. Finite and discrete. Finite falls into the category of discrete, but discrete is finite or infinite as long as it's not continuous. So is this continuous or is this discrete?
this is continuous?
So it's actually both. You see, the actual physical glucose levels is continuous. It can be any number. But when I measure it, whatever measuring device I use can't give an infinite decimal, right? It can only give like 90 or maybe to the first decimal or to the second decimal and so on. So the amount is technically continuous, but the way we measure it is discrete. So if I was answering this question on a test, I would write all of that and say, technically it's continuous, but when it comes time to actually measure it, it's discrete, something along those lines. Does that make sense? Yes, no, maybe so.
Yes.
You don't like the answer?
No, it's okay.
Okay. All right, part D. Express your answer to part B in mathematical notation. Express your answer in part B in mathematical notation. How would I write that the probability of the shaded region is about 3%, given what they gave to me in part C? The probability that capital X is less than or equal to 90 is equal to 0.03, 3%. Does that make sense?
Yes.
Everyone?
Yeah.
I'm here for you guys. Okay,
Yeah.
I need. Okay, so that takes us to the end of the chapter 15 review. There is some additional practice, but I will leave that for you. So let's go back now to the previous next chapter on the list, which is chapter 11. Unless there are further questions on 15.
What page are we on?
You mean in the workbook?
Yeah.
Well, I'm going back in the workbook. I'm trying to find chapter 11. I left my workbook and my textbook in school, so I don't have it here. But does anyone recall what 11 was about? I think it was 8 and 9 was on sampling. Yeah,
It was about the
Intro
basically.
to probability.
I'm sorry, say again, please.
Intro to probability.
Oh, it was more. Wait, so what was 15?
Probably probability. This one we had like how many people needs to be in a room to have 100% chance that 2 or more have the same birthday.
Right,
Like
that's probability. Okay. So what was 15 then?
It was sampling distribution for proportion.
Oh, wonderful. Oh, okay, beautiful. So my apologies then. When I called this a 15 review, this actually was 11 review. And now we'll do the 15 review. My apologies on that. I left. I don't have my high school this week, so I accidentally left all my textbooks there. So so thank you for reminding me. Okay. So now the chapter 15 review, which was the sampling distribution. We spent some time on this, talking about, we went to that applet to see how the distributions change when you have more than one at a time. So let's now do, this is now page 75 in the workbook. Introduction to statistical inference, sampling distribution. So question 1. It says, consider the population of all the M&M milk chocolate candies manufactured by the Mars company. Supposing that you want to learn about the distribution of colors of these candies, but that you can only afford to take a sample of 50 candies. And at first, we are only focusing on one particular color, say green. So the population is all M&Ms in the universe, all M&Ms ever made. And the sample is size 50. So take 50 M&Ms, disregarding the colors, just take 50 M&Ms. The number that you have now is your sample size, 50. Count the number of green candies, what we're going to call successes in your sample. So number of successes, we're going to call X. Number of successes is X. In this case, X greens. Now, does anyone happen to have any M&Ms with them? Probably not.
I actually do, but it's the yellow one. I don't think it has any greens in it.
Really? Well, that just ruins everything. Okay, well, without the actual numbers, we can still answer the following questions. Question A. Is the proportion of green candies in your sample a parameter or a statistic? Is the proportion of green samples in your sample a parameter or a statistic?
Parameter.
What's the difference between a parameter and a statistic? Remind me, please. I forgot. It's been so long.
Isn't a parameter a true proportion and then statistic a sample proportion?
Well, maybe, but that's not how we define parameter. I mean, that's correct what you just said. But how do we define parameter and statistic? What was the
Parameter is usually not known.
That's true, but again, that's
Oh,
not how we
it's
define-
a number that characterizes some aspect of the population.
Okay, a parameter is some number that characterizes some aspect of the population. And what's a statistic?
It's of the sample.
It's some number that characterizes some characteristic of the sample. So the proportion of green candies in your sample, parameter or statistic?
Statistic.
Statistic, right? It's about the sample. What symbol do we use to represent it?
P and P hat.
So P and P hat are different. What is the difference between P and P hat?
P is the parameter and P hat is the statistic.
Yes, P hat is the symbol that we use to represent our sample proportion. This is the sample proportion, which we know because we have our sample. And this is the population proportion, which we don't know and we'll never know because we don't have access to the entire population. Now it says calculate the proportion for your sample, but the truth is the best we can do is a formula for it. What is P hat based upon this? What's the formula for P hat based upon what I gave you?
Would it be 50?
50 is not a proportion.
Oh, would it be 0.5?
Nope, because we don't have the number of successes, so I'm not looking for a number here.
Okay.
What is the proportion of successes in our sample?
Would it be X greens divided by the sample size?
What is the sample size?
50.
So X over 50 is what I was looking for. The sample proportion is the number of successes. In this case, it's just X, a symbol that represents this value, divided by the sample size, which is 50. Does that make sense?
Yeah.
Yeah.
Okay. Part B, is the proportion of green M&Ms among all chocolates, milk chocolate M&Ms manufactured by Mars a parameter or a statistic?
Parameter.
Parameter. And what symbol do we use to represent it?
P.
P. C. Do you know the value of the proportion of green M&Ms manufactured by Mars? Do we know that value?
No.
No, we do not know that value. D. Clearly, you and the other students in this class, each of you take your 50 M&Ms and count how many greens. Each of you are going to get different values for your sample proportions. What important statistical term refers to this phenomenon of all of us getting different values for our samples? And just so you know, on the test, I will not be asking any, what term is this, what term is that? That's not how I roll.
Is it the law of large numbers?
The law of large numbers says, as the sample size increases, the sample proportion approaches the true proportion, right? Agreed?
Agreed.
But that's not what this is saying about everyone in the class getting different values. Right? Agreed? Yes, no, maybe so?
Yeah, I see what you mean.
Yeah, so this one, and this is what I'm pretty sure they're looking for, is the sample distribution, which is the idea that while the population has its own distribution, which is the possible outcomes with the various probabilities, samples also have a distribution, the various outcomes with their probabilities, which means everyone takes samples where it might get different results because different possible results for samples have different likelihoods. We're not all going to get the same number every single time. I'm pretty sure that's what they're looking for. And E we can't do because it actually requires us to actually have data. So we're just going to skip that one. And we can't do F because it comes from E. But we can do G. G says, if every student were to estimate the population proportion of green candies based on what you get for his or her sample, would everyone arrive at the same estimate?
Can you repeat that, please?
Sure. If everyone were to estimate the population proportion of green candies based on the proportion that each person got in their sample, would everyone arrive at the same estimate?
No.
No, I mean, if everyone gets different values, we're all going to estimate it in different ways. Right?
Yes.
Right? So certainly not. H. Even though sample values vary depending on the sample, there's still a pattern in the variation. In other words, we still have a distribution. We still have a graph that says the samples are likely to be here, not likely to be here. We saw that on the applet, right? We saw that while one at a time had its own shape, samples of 2 at a time or 3 at a time or 4 at a time, they each had their own shape as well. There are patterns to the variation. The more samples you have, the better, the more accurate of a picture that you see. So since it is time consuming and possibly fattening to literally sample more candies, we can instead use a computer to simulate the process of sampling. Of course, the problem here is that for the computer to do it, it has to have values for each color and how likely each one is. So it says here below are the graphs of some sample distributions for 100 M&Ms at a time and also 200 M&Ms at a time. The bottom one, as you can see here, is 100 at a time. The top one is 200 at a time. Do these sample distributions appear approximately bell-shaped? Do they appear approximately bell-shaped?
Kind of.
Kind of. I don't know what H was. There was really no H. It just gave me some information, but I. So yeah, I sort of. Okay, and I would say yes. I would say if I had to, if you had to give a definitive answer, I would say, yeah, I can certainly see a bell-shaped pattern in there. It's not perfect, but I can kind of see it.
It's
What
more
can you-
perfect on the 200, I guess.
I'm sorry, say again, please.
I mean, it's we can see it more on the M200. It's
Oh, certainly, but remember also that
yeah.
as we saw in the applet, as the sample size gets larger, the closer to normality it gets, right?
Yeah, sure.
So 200, it should be more normal than the 100. Not only more normal, but also we saw that it gets tighter,
100%. Yeah.
right? Okay. So what can you say about the means of the sampling distributions? Based upon what they give us. Remember, they are sampled, so don't expect the exact same values, but what can you say?
They stay relatively similar.
They stay relatively, I love that. They stay relatively similar. They're about equal. So roughly the same. Which again, as we saw in the applet, was something that we noticed to be true for all of the populations. And what about the standard deviations? What do you notice about those?
They get smaller and smaller as you get bigger and bigger sample size.
Yeah, so look at the values we have here for 100 and 200. As you can see, for 200, the standard deviation is roughly a third smaller, 0.03 to 0.02. It's a big decrease. So standard deviation gets smaller. Agreed? Yes?
Yes. Yes.
Okay, next. The Mars Company milk chocolate M&M's formula specifies that the proportion P of green candies they manufacture is, and it says your instructor will provide the answer, or you can find out by Googling M&M color distribution. So I'm going to do that because I don't eat M&Ms. So M&M color distribution. It says here 16% of them are going to be green. So what is equal to 16? What symbol, or 0.16? What symbol should be equal to 0.16?
P.
P, excellent. Not P hats, but P itself. The actual proportion of greens made is 0.16. Now, assume the company is telling the truth. Then what is the mean of P hats?
Should be close to 0.16. Right?
It is 0.16. The means are the same.
Okay.
Okay, because remember, the mean of the sample distribution is the same as the mean of the original distribution. Now, what is the standard deviation of P hats? Yeah, can we do this? Yeah. What is P hat standard deviation equal to? I gave you this formula last time, I think. I'm pretty sure. What's the formula for the standard deviation of P hat?
It was the standard deviation divided by the square root of n.
And what is the standard deviation of the original? Specifically for a proportion. I gave this to you. I know I did because I didn't do it for any of my other classes. They haven't gone this far. So I know it had to be you guys. What was the formula for the standard deviation of a proportion?
Is it the square root of P times 1 minus P
Over?
over square root of N?
Yeah, what you can put into one, you can put into one yourself. So it's equal to the square root of 0.16 times 1 minus 0.16 divided by n. Of course, n change. Oh, they want you to do it. No, just n. Okay. So what is 1 minus 0.16?
0.84.
0.84. So the square root of 0.16 times 0.84, we get 0.3666 over the square root of n. Now, if they actually give me n, like they do here, they say, oh, take n to be 50, then what would the standard deviation be? When n equals 50, standard deviation of p hat becomes what? Anyone there?
It would be 0.052.
Okay, I'll give a couple more, 1/8. And how about when n is equal to 100?
Point 0.03666.
And how about when n is equal to 200?
Point 0.0259.
Now go back to the previous page. Is that what we get for the standard deviations for n equals 100 and n equals 200? Come on, guys. This is just looking at the previous page and saying, hey, they're the same. Who's here? Who's paying attention? I don't understand.
Sorry.
Can I get a check here? Put me something in chat if you're actually here.
They are the same, or approximately the same.
So come on, guys. Let's verbally participate.
So the N200, when we did it here with the p hat, it's 0.0259, where there it's 0.02567.
Well, remember, they're going to be samples. So just because we expect it to be this doesn't mean every sample is going to give exactly the same value.
Yeah, I think it's fine.
It just means it's in the ballpark.
Yeah.
Yeah. Okay. 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 Oh, there's more. Oh, this is one over here. And we can't do K because I don't have a particular p hat value. Okay, so let's go. Let's go to the next page, page 79. And let's do more of these. So here's a question 1 again. It says, you're attending a large party at a Las Vegas casino. At the front of the room, there's a large jar filled with exactly 10,000 poker chips. So we have a jar with 10,000 poker chips. N equals 10,000. This is the population. So not even N, it was a capital N equals 10,000. Some of them are red and some of them are blue. The host announces a contest to guess the proportion of red chips in the jar. Anyone who whose guess is exactly right wins $500. You could make a wild guess, but to increase your chances of winning, you can purchase a sample of chips from the jar and see what proportion are red in your sample, which of course are then returned to the jar for the next person. Suppose you buy a sample of 100 chips for a cost of $25 and you find that 32 of them are red. First, what is your p hat?
%32%.
32%. It's 32 over 100. So if I had to guess what my P was, what's the best guess I can make?
would we use the equation? Oh no, it actually 0.32.
It will be 0.32 because remember, you use your sample value as a way of inferring information about the population. If the value from your sample had nothing to do with the population, what's the point? But if my sample is 32% red, then my best guess for the population of all chips is 32% red. In which case, how many red chips are there?
They're saying 32.
No, not 32,
200.
3,200. Because there's 10,000 chips, 32% of them are approximately red. So if I were to then guess to win this $500, I would get something in the vicinity of 3,200. Does that make sense?
Yes.
Is this
Yeah.
guy a statistic or is that guy a parameter?
That would be a statistic.
Statistic. How about that one? How about P?
A parameter?
That's a parameter. That's about the entire population. I'm only guessing it's true, but whatever it is, that is a parameter. Now B. Before a person purchases a sample of chips, the jar is twisted, turned, and shaken many times. Why is this important?
It makes sure the sample size is random.
Yes, ensures randomness. Ensures randomness. As it turns out, many other people at the party buy their own samples of 100 chips. Needless to say, they don't all get the same proportion of red chips as you did. What is the important term that describes the fact that these different samples would produce different results?
Sample distribution?
Hey, you were listening. Sampling distribution. D. The 10,000 chips in the jar represent the population here. What is the population parameter?
$10,000?
Well, 10,000 is a sample size, right? But for this example, it's not what we're looking for, right? What we're looking for is not.
Oh, all the chips that were made then?
I'm sorry, say it again.
Would it be all the chips that were made like red and blue?
Again, what are we looking for in this problem?
Is it 1 to
The red?
10,000?
I'm sorry, say again.
Is it 1 to 10,000 or no?
No, it's one number.
3,200.
Well, 3,200 is our guess for what that number is. But we don't know the number, right? We don't know population parameters, so we can only describe it in words. What is our description of the population parameter?
The number of the 10,000 chips that are red.
Yes, either the number of the 10,000 chips that are red or the proportion of the 10,000 chips that are red, because if you know one, you know the other, so they go hand in hand. Okay, the population parameter is the proportion or number of these 10,000 chips that are red. Now, E. Suppose that the jar actually contains 4,000 red chips. What is the value of the population parameter? So because of this question, let's go back to the previous one. It must be the population proportion that they were looking for and not the number. See, D was a little vague. It could have been both. But based upon E, it must be the population proportion. So what is P based upon what they just gave me in part E?
0.40.
0.40, 40%. Write an equation with a symbol for the population parameter on the left and its value on the right. Okay, I just did that for you. F. 20 party goers in all bought 100 chip samples. Here is the dot plot of the various proportions of red chips they obtained. So 4 people actually got exactly 40%. One person got really low. It looks like 28%. It says use the information in the textbook to determine the mean, standard deviation, and shape of the sampling distribution of p hat, and round the standard deviation off to 2 decimal digits. How would I find the mean? How would I find the standard deviation? And what is the shape?
Find the mean, you would just add them all up and then divide it by the number of samples you have.
100%. To find the mean, I add it all up and divide by how many I have. So let's do this quickly. 0.28 plus 0.32 plus 0.34 twice plus 0.34 twice plus 0.36 246. Oh wait, 0.32, 0.34. Oh, I did it twice. Okay, 0.36 twice plus 0.38 3 times plus 0.44 times plus 0.42 twice plus 0.44 twice plus 0.46 twice plus 0.48 once, and then I divide it up by 20. So I get my mean is 0.393. How would I find the standard deviation? If I really wanted to. I don't want to, but if I did want to, how would I find it?
Wait, what did you do? You plug in the values in your calculator?
That's probably even better.
Mhm.
So I'm gonna go to my stat, edit, and let's see, 0.28. I'm gonna use list 2 for my frequency. So 0.28 and then 1 time, 0.32 and then 1 time, 0.34 and then twice, 0.36 twice, 0.38 3 times, 0.4 4 times, 0.42 twice, 0.44 twice, 0.46 twice, 0.48 once, and let's delete that number. Okay, so when I put it in, I get this. I have my first column is all my different data points, and my second list is how often each of them occurs. So when I go to stat, calc, 1 var stats, it says list L1, it says frequency list. I'm going to put in L2 for that, and I'm going to calculate. And it gives me a mean of 0.393 and a standard deviation to 2 significant digits of 0.051.
Could you use one line if you write out each number individually?
Sure, of course. Yeah, I think we'll take a
Professor,
little
where do
longer.
you go to do the standard deviation? So you go to calc, and which number is it again?
The first one, 1 var stats.
Oh, I see. Okay.
But you
Can you
gotta make
just
sure,
click
you
on
gotta, if you do it my way, you gotta make sure that your frequency list is L2. If you
I
just
see.
do, if you do every number individually multiple times, then you have to leave frequency list blank.
I see. And then you go down to calculate, and then you hit enter.
Yeah.
I see. Okay.
Now, what shape would this be? What shape is this?
Can we graph it or? Oh, I guess not, huh? Normal
But-
distribution.
Huh?
Normal distribution.
Yeah, it certainly looks normalish. Certainly looks normalish. Maybe an outlier on the left, but certainly it looks normalish. And if we use, I mean, that comes from the actual data. If we just use pure theory, the mean should be 0.4 because the mean of p hat should match the mean of the original. How do I get the standard deviation by theory?
.1
Yeah. How do you get that?
because the 0 and then there's a 5 next to it. When it's 5 and up, we just add the number.
No,
Like
no,
the 0
no.
turns out to be 1, but that's how I did it.
No. We have a formula. We had the formula up here. It was this one right here. Right? We had a formula for calculating the standard deviation. You multiply your p, which is 0.4, times 1 minus p, which is 0.6, divided by n, which is 20, and take the square root, and you get about 0.11.
I did all that in my head.
You got that in your head? That's very impressive. I wish I had that ability. But alas, I don't. Anyways.
I'm just joking.
Oh, well, how did I know? I mean, people can do things other people cannot. I didn't assume any less of you, or more of you, or equal of you, or anything. I'm not even sure what I'm saying right now. I'm just really tired. So moving forward, although I think that's pretty much it.
That makes two of us. I'm really tired too.
Huh?
I said that makes two of us. I'm tired too.
I'm exhausted. I'm just looking ahead. Okay, only one more question. So let's do the last question, number 2. It says, suppose that the casino announces that in addition to awarding the $500 prize, anyone whose guess is within 5% of the actual value will get $25. So A, about what percent of the people who buy samples of 100 chips would you expect to get their money back? Use the 68, 95, 99.7 rule. What percent of the people who buy samples of 100 chips would you expect to get their money back?
Wait, what percent of people who buy 100 chips would get their money back?
Yeah, what percent of people would be within 5% in either direction of the true value? So if we know that it's normal or approximately normal, whose center is 0.4 and whose deviation should be 0.11, actually, the deviation would be, what's the deviation? It's not, if we have to go back for this one to one person at a time, we're not looking at all 20 together. We're doing one person at a time. So the deviation is just P 1 minus P. So what do we get for that? The square root of P times 1 minus P. That's 0.49 in either direction. Or about 0.5. We'll say approximately 0.5. Jesus. 0.4 times 0.6. Does that make sense? P times 1 minus P square rooted is 0.5. So I think so it must be over it. Otherwise, it makes no sense. So if the deviation is 0.1 in either direction, so we know the true value is 0.4, correct? The true value is 40%. That's what they gave us above here. Where are we? The true value is right here, right? The true value is 40%. If you're within 5% of that, we'll give you $5, which means from what percent to what percent gets $5? $25. Jeez, how do I turn this off? Okay, so if the true value is 40%, and if you're within 5%, you're gonna get $25 back. Between what value and what value do you get 25, you get $25? From where to where?
0.35 to 0.45.
0.35 to 0.45, correct? Right?
Yes.
So how far out do I gotta go to reach 0.35 or to 0.45? How many standard deviations do I gotta go?
A lot.
Well, if the deviation is 0.1,
0.1, never mind. I was thinking 0.01 for some reason.
yeah, if the deviation is 0.1, then it's actually half of a deviation, correct? So I gotta be honest, I'm a little confused what you mean by the 68, 95, 99.7 rule.
Did they expect us to use a calculator?
Yeah, but the thing about the 68, 95, 99.7 rule is that you don't need a calculator. That's what you do in your head.
Oh, okay.
If it's not one of those values, then certainly you can use a normal CDF and you can get the exact value. So I have to admit, I am a little confused by this. So I'm gonna think about this one and try to figure out what I'm not saying because I'm a little confused. And we're gonna stop here because this is the end of the chapter anyway. And I think it's it for today. It's been a long time and a lot of work, and I think people are fading. I know I'm fading. Anyone else fading?
Slowly.
I'm fading a little bit. So we'll stop here. I'm gonna pause.